Hi, everyone. Hi. Thank you so much for joining us here tonight for this iteration of our new faculty lecture series. Can you hear me? Yes. Okay, great. My name is Patricia Rintgemma. I'm the Alumni Engagement Officer for the Faculty of Science. It's my pleasure to welcome you all here. Before I go through a couple of housekeeping items, I'd like to take a moment to acknowledge that much of our work here at the University of Waterloo takes place on the traditional territory of the Neutral, Anishinaabe, and Haudenosaunee peoples. Our main campus is situated on the Haldeman Tract, the land granted to the Six Nations that includes 6 miles on each side of the Grand River. Our active work towards reconciliation takes place across our campuses through research, learning, teaching, and community building, and is coordinated within the Office of Indigenous Relations. Our new faculty lecture series was created with the hopes of showcasing our newest faculty members and the incredible research and teaching that happen here at the university. I'm very excited that this edition also happens to showcase the faculty's new dean, Dr. Chris Hauser. I'd like to also recognize that there is several other faculty members in attendance tonight, including our Chair of Biology, Kirsten Mueller, our Chair of Chemistry, John Corrigan, and our Chair of Earth and Environmental Sciences, Mario Caliglio. It is great to see so many familiar faces. It's always wonderful to welcome our alumni back to campus, so thanks again to you all for coming. But before we get to the main presentation, I'd like to go over a couple of quick housekeeping items. So the washrooms are located outside of the lecture hall, way down the hallway in QNC and to the left. While this presentation isn't being broadcast virtually, it is being recorded and will be available at a later date. And lastly, there will be an opportunity at the end of the presentation to ask questions, so please feel free to hold on to those until the end of the presentation. With that, I'm going to introduce you to Dr. Mario Caniglio, Chair of the Department of Earth and Environmental Sciences, who's going to give us a quick update on the department and its current initiatives. Dr. Caniglio's research on sedimentary rocks has led him to travel all over North America, including the Arctic, as well as the Caribbean, South America, and the Middle East. He served as the Associate Dean of Science for Undergraduate Studies from 2005 to 2013, and then as Associate Vice President Academic until 2019. And since 2021, he has been the department chair. Welcome, Mario.
That's great. Thank you, Patricia, for the introduction. Good evening, everybody. I'm really pleased to see you, and I'm very much looking forward to introducing our new faculty lecture this evening. Our speaker tonight is Professor Chris Hauser, and I'm pleased to tell you that even though he recently came to the University of Waterloo to be our faculty dean, he is also the newest member of the Department of Earth and Environmental Sciences. So before I introduce him, indulge me for a minute or two while I tell you a little bit about our department so you can better appreciate the role we play in the faculty and as well as externally. I may be biased, and I most certainly am in this respect, but I can't think of a Department of Earth Sciences that has the breadth of talent that we have all in one place. And I'm referring to faculty, staff, and our students as well. The Department of Earth and Environmental Sciences is known for its interdisciplinarity, its cutting-edge geoscience, and the innovative approaches to some of the most pressing issues facing humanity today. Our faculty focus on earth and environmental sciences, sometimes quite obviously through a lens of a physicist, a chemist, a biologist, an engineer, a mathematician, or even a computer scientist. We have a diversity of top researchers contributing to the study of global climate change and the myriad of entangled issues that are associated with that. Ground and surface water interaction, looking at supply and quality, as well as the impacts on aquatic ecosystems, natural hazards of all sorts, including landslides, renewable energy and earth resources, including the critical materials that we need to electrify our society and move away from fossil fuels. And last but not least, various aspects of our Earth history as it manifests through the biological, physical, and chemical evolution that our planet has seen. These are all incredibly important research areas, and we have to understand so as to ensure our planetary home remains healthy for humans as well as all the other creatures that live on this planet. Our department has 26 faculty and 17 postdocs and research associates, 7 permanent staff, and about 40 research staff. We have 38 PhD students, 40 master's students, and 285 undergraduates enrolled in the variety of programs that we support. That is geology, geophysics, hydrogeology, and water sciences. Quite a few of our faculty have been recognized by national and international level awards. It's rare that a month goes by when I'm not writing an email congratulating them on their latest achievement. And our postdocs, our graduate students, and our undergraduate students also regularly attract awards and scholarships of various sorts. Together, this concentration of talent means that we as a department really punch above our weight when it comes to research. This year, our research income was just slightly over $11 million. 85% of it derived from federal sources, and the balance from provincial, industrial, and other funders. So now, let me tell you about our newest faculty member and our new Dean of Science. Professor Chris Hauser obtained his bachelor and master's degree at the University of Guelph, and later went on to the University of Toronto, where he earned his PhD in geography. He worked as an assistant professor at the University of West Florida from 2004 to 2007, moving on to Texas A&M University College of Geosciences in 2007, where he was then appointed later on as a full professor in 2016. In that year, he moved to the University of Windsor to be the Dean of Science and professor in the School of Environment over there. His service has included a variety of significant academic leadership roles. At the University of Windsor, he was interim vice president for research and innovation and Dean of Science for 2 terms. At Texas A&M, he was associate dean for academic affairs and faculty development and the global faculty ambassador. Chris leads the coastal research group out of the University of Windsor, which studies sediment transport and nearshore morphodynamics with a focus on beach-dune interactions and barrier island responses to sea level rise. Chris is presenting tonight our new faculty lecture. Please join me in welcoming our new Dean of Science, Professor Chris Hauser, as he informs us on the state of our shorelines. Chris.
Okay. Perfect. Thank you, Mario. And I do appreciate the fact that I can pretend that I'm a new faculty member at this moment and starting with a new academic position. And what I'm going to be presenting on tonight is an overview of some of the research that we are doing from Costa Rica to the Gulf of Mexico to the Maritimes and ultimately to the Great Lakes, looking at what is happening to our shorelines. Now, my background in terms of the science that I do is called coastal geomorphology. I look at how landscapes change, how sand is moved, particularly amongst the near shore, the beach and the dune, and what that ultimately means for coastal barriers in the future and what's going to happen to them. Are we going to see them erode away? Are they going to survive and be resilient? And how do we actually manage that? And I'm going to be showing you, again, it's a very high-level overview of the research, and I'm going to be showing you a lot of drone imagery as we go through this. And this particular one here is from Brackley Beach in Prince Edward Island. It's one of my favorite beaches in the world. And this is where we are doing a lot of work understanding how sand moves across these 3 systems, the near shore in the water, the beach, that kind of area that is somewhat dry and somewhat wet during the year, and ultimately into the dune. And that dune is one of the most important things that we have because it's a wall of sand and it protects us from coastal storms. It protects us from the storm surge. And I'll be talking about Hurricane Fiona in a little bit. Now, where I really started working on coastal barriers was in Pensacola, Florida, when I moved and began working at the University of West Florida. And I moved there with a 6-week-old the day before Hurricane Ivan hit. Now, doing beach erosion, having a hurricane hit that day when you start a new academic position is the jackpot when it comes to funding, when it comes to publications. And in that year, we had Ivan, Arlene, Cindy, Dennis, and Katrina all hit within tropical storm winds, which means that the entire barrier system was obliterated. This is the Fort Pickens area of Pensacola on the Gulf of Mexico. At the very end of that is the actual Fort Pickens, where Geronimo was held for many years, and it was also a major part of the Civil War. And this area was just completely decimated. And because of this work, and we use what we call LIDAR. LIDAR is a laser-based system that is shot out of an airplane, and it gives us a full three-dimensional image of what these coastal barriers look like. And because we hit Hurricane Ivan at that exact moment and all these other storms, it was great to look at the erosion. But erosion is only half of the problem. This is where people, in particular there was people from Louisiana State who would fly in right after Hurricane Ivan and Katrina, and they'd take these amazing shots of how the beach eroded. In the end, that's irrelevant. What's more important is how does this actually start to recover? How does the sand get back to the dunes? How long does that take? And what we found was the first data to show that in fact it can take upwards of a decade for the sand. So what was actually 5 hours of one storm takes 10 years to come back. Now that becomes a big problem when we start to think about the resiliency of these systems, and it's the one reason why we run a program called Coasty. This is in partnership with Parks Canada, and this is a citizen science program where you put your phone into a cradle and you take the same shot that everybody takes on that beach. And we are close to 5,000 photographs in a year and a half. And it's from around Parks Canada sites, particularly in the Maritimes and Ontario, and we're moving to British Columbia later this year. And it's because, and so as I said, in terms of it's distributed, so it's mostly in the Maritimes right now. We also have sites at Point Pelee, as well as the Bruce Peninsula and Puckasaw up in Lake Superior, but we are moving to British Columbia and the Pacific Rim, as well as up into Nunavut next year with these sites, and it provides us unprecedented access to coastal sites. And the reason why this is important is that myself and one other faculty member who just happens to be across the road at Wilfrid Laurier were the last two coastal erosion people in all of Ontario. And if you look at all of Canada, there's 5 of us. We have the longest coastline in the world and the smallest number of people who are actually studying coastal erosion. So the more people that participate through our program in Parks Canada, the more eyes, the more scientists that we are able to work with. And it's because of that that we were able to see what happened with Fiona. And so if you saw the National on CBC, you would have seen these photographs before. This is the coasty shot just before Fiona at Brackley Beach, that one you saw in the drone shot before. This is the day after. 15 meters of dune was lost in just a couple of hours. And what we have seen today, and this is just yesterday, that's all the sand that's piled up. Now that looks like quite a bit compared to this. That's piled up because it's sitting behind a boardwalk. It's sitting behind an obstacle. If you actually look further down, the dune has hardly recovered whatsoever. We're looking at several years before these dune systems recover. Cavendish, this is the Anna Green Gables site. Here's before, here's after, and that's yesterday. We just aren't seeing the recovery. The problem is not necessarily that these storms came through, is that last week was Tropical Storm Lee, and it was bearing down towards Nova Scotia and PEI. Now, I'm a coastal erosion person, so I actually want the storms to go right because I need that up my site. But if it hit on Prince Edward Island, these dunes would have been gone, because that was all that was required to take them out. What we're going to see over the next couple of years is unprecedented in the number of storms that are going to hit, how quickly these dunes erode before they can begin to recover. But one of the bigger obstacles is not the hurricanes, the big news story. It's the one you actually don't hear about, and that is sea ice. This used to be where in December, all the way through to March, this would just be ice, and it would protect the shoreline, the dunes, from winter storms. Last year, there were 3 days when there were ice on this beach, which meant that every winter storm was able to come up and hit the base of the dune, and any recovery that we saw right after Fiona was gone. So it's not the big storms, it's not sea level rise, it's sea ice. And I'm going to show you a little bit later that lake ice in the Great Lakes is one of the biggest problems that we face. Now, how do we deal with something like this? And this is something called managed retreat. In a natural environment like this one, it's fairly easy. These beach dune systems are naturally dynamic. The sand gets taken off into the water, it comes back by the wind, the dune grows, and every time the sea level rises, the storm comes through, the whole thing migrates landward. Again, in this drone image, it's easy. There's nothing back there. It's just protected areas, protected dune environment. So therefore, these dunes, this beach can move backwards. But in the vast majority of our coastlines, what's behind there is infrastructure. It's roads, it's buildings, it's properties, it's livelihoods. In order for these coastal systems to be able to be resilient with sea level rise, changes in storm activity, and the loss of sea ice, you're going to have to require that people are going to lose their land, they're going to lose the roads, their houses. That's a very difficult management question. And this is managed retreat. Allowing things to move backwards is what we're also going to face in the Great Lakes. Apologize for the last little drone turn there. Now, I'm going to go off the Coastie program here. I'm going to come back to managed retreat in a little bit. I'm just showing you a little bit of what we do. Next year, the Coastie program, we're really proud to say, is moving into glaciers. So with BC Parks, we're actually going to have Coastie stations, I guess they're going to be called icy stations, at each of these glaciers in which people are going to help BC Parks be able to record glacial retreat in real time. Now, one of the other areas, and one of the things that we capture through Coastie, is rip currents. Now, when I was doing my undergraduate and in the grad work, I didn't even really know what a rip current was, and I'd never been in one. But when I was working in Pensacola, Florida, I was working on a beach, and I was working with one of the coolest instruments that had been around. It was basically the backup sensor on your cars today, which is standard. But at that time, it was brand new. And we could measure 0.5 millimeter changes in the surface. So I could watch individual grains of sand being deposited and eroded with every wave that went up the beach and down. I thought this was cool. We sat there for 6 weeks, measured every wave for 6 weeks. I get to sit on beaches, so it's not that bad and not that boring. But while I was working on that beach in Pensacola, I watched a family put their kids directly into a rip current. And so I ran over and got the kids out of the water and started talking to the parents. And this started an entire area of research related to rip currents and beach safety. And just for sake, that's a person walking on the beach. That is a rip current that is moving at about 1.5 meters per second. Most kids that can swim are around 0.75 to 1 meter per second. This is faster than most kids can swim. And I'll show you the fastest rip current in a second. So this is the beach there I started to learn about rip currents and really transformed my research, which has also come back to the Great Lakes. That's a rip current right there, that dark water. There's another one, there's another one, there's another one right there. Look at the boy, the little girl, this family. They're right at the edge of a rip current about 1 meter per second on this particular day. I happened to move to one of the most dangerous beaches in terms of the number of drownings. This is what it looks like from the air on a drone shot. Each one of these little blank spots is a rip current. Each one of those little dots on the beach is somebody. Look at where they're positioned. They're right there, rip current. They're right there, rip current. They're right there, rip current. The reason is that people, when they go to the beach, they want to find the spot that's deepest, because when you go into the water, you don't want to go 100 meters offshore to finally get to chest deep. You want to go just a few meters. So they will purposely pick a rip current because it looks calmer, there's no breaking waves, and it's deeper. This beach, on average, has about 10 to 15 drownings per year. This is what a rip current looks like from above. This is a non-toxic dye that we put in. Just to give you an idea, you can't even really see them. That little dot right there where my pointer is, that's a person. This rip current in Australia It's caused by the waves breaking. So when a wave breaks and it comes towards the shoreline, wave is coming towards the shoreline, it starts to touch the bottom, and as a result, it gets taller. And as it gets taller, the orbital velocities, imagine my head is spinning at this moment. The orbital velocities get faster than the actual wave. And as a result, the wave flips forward. And when it flips forward, it throws water. Throws water forward. Most of the time, on most beaches, it goes straight back offshore as something called undertow. Something that is diffusive. It's relatively weak, and it really is at your toes. But wherever you have a variation, and there's a bar here, and there's a bar here, and there's a break in the bar, instead of going back as undertow, it goes to the side and goes straight out as a rip current. So all that very loose, very slow current is concentrated into one location. When it's undertow, it's at your toes. It doesn't take you under. You actually don't feel it. Nobody drowns because of undertow. Where they drown is a rip current because when the water comes to that center point, it comes towards you at your chest. That's where you're the most buoyant. And so when you're standing in waves, and you're going up and down in the wave, and the wave picks you up and it's pushing you back, the next step, you're into deeper water. And when you get into deeper water, you're trying to touch. So now you're on your tiptoes. And you get pushed back even further. Now you can't even touch the bottom. And when you get into water that you can't, that's too deep for you, your natural tendency is to keep your feet down. When you keep your feet down, the water is right here. You're now desperate, you're anxious, and your mouth is open, and the water goes into your mouth. So rip currents are a problem because they're concentrated, very fast flows, and they're right at your chest. They're not just related to marine environments. This is Lake Huron, just outside of Kincardine. Kincardine, I'm going to show you some examples from around the Great Lakes here, but there are natural rip currents that form on these beaches all the time. This is what it looks like from the drone. There's the walkover where you can get to the beach. That walkover is where I'm standing taking this photograph. The rip current is right there. You can't see it. It's hard to see it. And in fact, when you look at it, it actually looks like the calmer water, and people want to get into that. Where we have a large number of rip currents in the Great Lakes, they're called structural, and they're associated with groins and jetties. Now you've got a current moving along the shoreline, it comes into this location, and it goes straight out. These are very fast-flowing rips. They tend to be also very violent. It's like a little washing machine right there. But this is the problem. The mother and her young child on a slippery pier right beside a rip current. If they had slipped in, that little girl would have been out here. And then she would have been brought back to shore, but she'd have been able to swim at that time. Here's another one. This is Southampton. There is a rip current going straight off right here. But could you imagine falling into this water, being churned around? You don't know. So I've been in rip currents. I'm going to show you the one I've been in a second. And when I take students into the field, we purposely get into rip currents. Now, we wear life jackets, we have lifeguards on the beach, and we have surfers out in the water. But we get into these, and you're up and you're down, you're turning all around. You don't know what's left, right, up, down. You can't figure your way out. And when you get into something violent like this, it's really tough to be able to find your way out before you get out into the water. But this is one of the biggest problems. Watch this kid. I told him off 3 times. So I did the boomer thing. I just said I'm a boomer. Okay. I did the boomer thing of telling this kid, don't do this. But if you look at the sign very carefully, the sign's backwards. This is Kincardine. There was a drowning in Kincardine on this pier, on this side 3 weeks ago. A family just simply got into the water, and a grandfather and their young grandson got into the water. They just jumped like that. There's a rip current right there. People just ignore signs. In the Great Lakes, approximately 50 people a year drown due to surf. That means to waves and currents. The majority of them are young males, less than 30. Ontario has the highest proportions of drownings in the Great Lakes region. We only have 7 beaches in all of Ontario that have lifeguards. No other beaches have lifeguards. Kincardine has had many drownings, has 0 lifeguards. Most of those, about 30%, are attributed to rip currents, but that's what we know, that they were directly into a rip current. We don't have a lot of information about that. Now, COVID was a big year for us to better understand drownings. What we were finding, and these lines that extend above, those were the COVID years. So during 2020, when everybody was in lockdown, you couldn't go anywhere. So the moment the lockdown stopped, people got out of their house. You couldn't travel internationally. You couldn't really travel far, so you went to your local beach. And what we actually found is that drownings increased significantly right after COVID. And if you're going to a beach, you're going into these conditions, you're just being locked down. Why would you pay attention to a flag? Why would you pay attention to a lifeguard? And around most of the Great Lakes region, lifeguards were no longer on life-saving duty. They were on COVID duty, making sure that people were separated versus when they were in the water. So COVID created a spike in drownings, not only in the Great Lakes region, but across the world. Now, why that's important is that when you look at all the drownings in the Great Lakes between 2010 and 2020, it cost this region $1.1 billion US. Because most of them, are young males, less than 30. So if you think about the value of a statistical life, you've now lost an entire set of generations who are no longer contributing to the economy. And as a result, we have the direct costs and the indirect costs associated with it. The problem that we start to also face, and this is the original sign that was taken with that family in Pensacola, is that these signs are completely wrong. You probably have seen them across Canada, you've probably seen them across the United States. The image is wrong. And this is where I started working with psychologists and social scientists and opening up a new area of research. It's a view from nowhere. The watercolor is wrong. It looks rough there. It's green arrows, and the beach is in the wrong angle. This is what a real rip current looks like from the ground. Look at the difference between the sign. Now, NOAA said that they made these signs just to inform people how to get out, but just like a bird book, everybody used it as a way to identify a rip current. So they were being used incorrectly, and that family that went down to the beach on that first day used this sign and picked this location as an example. This beach here, this is Playa Cocles near the Panama border in southern Costa Rica. This is the fastest ever measured rip current by us personally in the water. It was moving at 3 meters per second, 9 feet per second. Michael Phelps' fastest time was 2 meters per second in a burst of energy. This is another example. This is Cavendish, again, Anna Green Gables site. That's a rip current right there moving at 1.5 meters per second. There's the sign. It doesn't work. So I was able to work with the NOAA rip current messaging team. We redesigned the sign, but they still got it wrong because it was a bureaucratic process. The beach is completely incorrect. But this particular new sign that is being distributed now is based upon our research. PEI has also taken it, but they've actually designed the beach correctly. And if you've been to PEI recently and you've seen these signs, they come directly from our work. But most importantly, and again, I'm going to come back to the sand here in a second, but I work in sand, I look at beaches and how they erode. The thing that I take home is that the work that we are doing is saving lives. So in Costa Rica, which I just happened to be working in many years ago, people approached me and said, can you send us a copy of your paper from Pensacola, Florida? And I sent them a copy, and I said, I'll do one better. I'll be at your office tomorrow morning to talk about rip currents in the country. And as a result of our work in Costa Rica, where a lot of those pictures were from, we now have a legislated lifeguard association. Every major tourist beach has to have a lifeguard present. And it's because of this simple work, that family that first went down. This is what I take home at night, that this is the thing that you can make the biggest impact on. We've done just a recent paper looking at the value and the cost of drownings in Costa Rica. On average, every drowning costs $2 million to the local economy. And it's a huge impact that they need to start to consider, because these lifeguards may combined get paid $20,000 a year. $20,000 a year versus every drowning is $2 million. Now, another area, I'm going to get into the Great Lakes here in a second. We also work a lot in vessel-generated waves. During COVID, because I couldn't get out, and I just sat at the cottage and sat on the dock, I started watching boats go by, and everybody was buying boats that year. And this is not the cottage, but this is on Lake St. Clair River. And we started realizing how much boat wakes were becoming a bit of an issue. And what we're finding is that boat wakes, when they come through, and this is just a simple cabin cruiser that went through, create a major spike in sediment transport. And that spike in sediment transport creates turbidity, and it is also contributing to nutrient loading within the river. Some of the work that we've also done in some of the kind of cottage country lakes, and wow, this video is very sketchy. I did lose the drone right after this video. I didn't realize how bad it was, because I'm driving the boat right now. That's my son in the back. My daughter is taking the video. But the next video, my daughter was driving, my son was water skiing, and I was flying 1 foot off the water behind him, doing this kind of ESPN type thing, except that I missed the wave. I hit the wave and shot my drone straight into the water. I've gone through a lot of drones. But what we have found in cottage country lakes, and this is where our cottage is, that 80% of all wave activity is generated by boats during the summer. And so as a result, you've got this increase in wave energy, you've got shoreline erosion, and you've got, again, nutrient loading within your lake. And this is something that we're hoping to be finishing up in this coming year, and we have about 600 different sites within Ontario. But now let me get to Great Lakes shoreline erosion, the main focus for tonight. Some of the work that we've been doing ever since I moved back to Ontario, looking at the problem of what's happening to our shorelines. And this is just an area to the east of Wheatley on Lake Erie, and you can see where the modern shoreline is, where the shoreline was in the 1950s, and the shoreline would have been out here before that time. You can see, and this becomes important, that these shoreline revetments, these wooden stakes that they had put in to save the original shoreline, simply did not work. Part of what's driving this is water levels. And 2 years ago, when water levels hit their historic high, there was a lot of discussion about that water levels are creating erosion within the Great Lakes. It contributes to it, but it's not the major driver. And that it does create coastal flooding. This is Wasaga Beach during 2020. And in fact, it was flooding directly into the shops right at the base, and they were trying to create this artificial barrier to protect the shops. The bigger issue is ice. This is Point Pelee at the maximum ice back in 2021, and this lasted for just a couple of weeks. During the 1940s, the ice cover on Lake Erie used to be thick enough you could drive a transport truck from Leamington to Rock and Roll Hall of Fame. What's it called? Where's it? Cleveland. From Leamington to Cleveland, you could drive a transport truck across. Now, hardly any ice is forming. As a result, this is a typical scene. This is, again, Wasaga Beach during the middle of winter, in the heart of February. There's no ice. That ice protects the water because it's stopping the waves, it protects the sand. This is another example. This is on the edge of Point Pelee, again, during February. This should be covered in ice. We just don't see it. And if you think about the temperatures of this week, think about how much they have been warming the lakes, which means your ice formation is going to be even later this coming year. As a result of the lake levels, the increase in range, and some of these storm surges that we're seeing in the winter, this is Riverside in Windsor. So this is the Detroit River. This is Lake St. Clair. This is the area that floods during the middle of winter with our now winter storms that come through. At high lake levels, this entire region of historic homes is completely underwater. And this is great, like no wake zone. This boy holding up as cars were going down through. This is the town of Tecumseh, so a little bit further to the east. This is what is being planned. This is work by Pete Zuzek, who is a coastal engineer, is that in the future, these areas in red are going to have more than 1 meter of water during the middle of winter, during these storms. So it's not just the lake levels, it's this increase in storm activity on top of the lack of ice. How do you protect against any of this? Most of them, what they're doing now is putting up barriers. So what had been a natural shoreline is now going to be a wall. The most extreme examples are from the Netherlands, where they've just basically walled the entire country, but places like Houston, which is where the majority of our oil refineries are in North America, they're putting up something called the Ike Dike. This is a massive, like tens of miles of a wall that they're going to put up that they can lift and lower the gate as the tankers come in to try to protect the city of Houston, which is sinking because of groundwater extraction. So most people, as I said, are putting up these walls, these rock walls. They don't work. Now, they do protect against this wave attacking right there, but you've gone from what was sand and silt to now these big boulders. That's great. But you think about it, these waves have energy. These waves have an appetite to move sand. If they don't have the ability to take sand from the shoreline, what they're doing is they're taking the sand from the bottom. And so in front of this rock wall, it is simply deepening. And eventually, it deepens to the point where the rock wall falls down. And we're talking about, for 100 feet, is about $10,000. So when this happens, you're just basically giving yourself about 10 years. But the other part to this is that when you start to protect these areas, again, this is Godrich, big rock wall. It's going to fail in a couple of years simply because it's now going to erode downwards. But anything that is downdrift along the shoreline from this location is going to be the point of erosion. So if I put up a rock wall, I'm going to stop erosion for about 10 years at my location. But now when the wave and the current gets over here, it's going to pick up new sand, which means now I'm going to have to put in a rock wall, which means this person's going to put in a rock wall and this one. So the moment somebody puts in a rock wall, a hardened structure, the next person down the line has to put one in or sacrifice their property, which means that these walls can't be done in small sections on individual properties. They have to be done over an entire stretch of shoreline where the sand is moving. And this is a great example. This is just outside of Kingsville, again on Lake Erie. Just look at how many properties have poured tens of thousands of dollars directly into their shorelines. And even some of the natural shorelines, it's rocked just to protect the farmer's field. And here you've got a natural shoreline, but look at how far back it's going. The trees are starting to fall in, and there it comes back out with these rock walls. These rock walls simply displace the problem in both time and in space. Another major issue that is affecting sand transport in the Great Lakes are groins and jetties. So this is Rondeau Provincial Park, beautiful spot. It was a depositional lobe associated with the glacial times, and it's got all these well-developed beach ridges, and it used to have a spit that would extend, and this is that spit here. The shoreline is way over here. Because of the jetty that they put in to allow boats to get into this harbor area, this has eroded back from about here. And as a result of that erosion, it's lost all of its vegetation, and it's just simply rolling over and slowly breaking its way through, which means that this entire spit area is about to get broken through, and the marsh and the habitat that's back in here is now going to be exposed to Lake Erie waves. This is an example. So this gets you back from 1923 in green all the way back to modern day. We are talking almost a 500-meter loss of the shoreline. I'm going to show you some other locations in a second that we're averaging 4 meters of loss per year. This is 500 meters between 1923 and 2018. Now, this is just because the sand is coming in this direction. It piles up right here and doesn't feed this area. As a result, this area is starved, it's eroding, and it's just simply eroding backwards. This is also something that we are seeing in Lake Huron at the Pinery. And Pinery is a major depositional. These are dune systems that are thousands of years old. And this was an old estuary environment, and the sand was coming from the cliffs way up at the top, and it was filling in. And these massive dunes formed. And now, this is the modern line. But this is what it looks like today. The dunes are completely eroding. Now, part of the problem is that these dunes were formed thousands of years ago, which means that they are historical features. They are not in equilibrium with current conditions in terms of waves, water levels, but they're eroding and they're valuable habitat. So this is what it's looking like today, and they're trying to figure out how it's going to come back, and they're revegetating parts of it. This does work, revegetation does work, but it stabilizes it in its given location, and it doesn't address the major issue right at the water line. These dune systems, they believe, are just simply going to migrate backwards. But there's no evidence of it. This model, which is being used to describe Pinery as a perfectly resilient site, comes from Prince Edward Island. Prince Edward Island is not the Pinery. This has wave activity, it's got sea ice at times, and it's got just a sea level rise that's relatively constant. The Great Lakes do not have a sea level rise. What they have is a slow rise, and then an immediate plummet, and then a slow rise, and an immediate plummet. So they go through these cycles. But as a result of that, the sand that gets taken out of the dune gets put into the bars, and the bars at Pinery are moving offshore. And as a result, the sand here will, in fact, never come back. But to add to that, the sand used to come from bluffs. So this is just north of Grand Bend. The bluffs are eroding. This is a natural supply of sand that would get its way down to the Pinery, and maybe it would protect it and keep it stabilized. The problem is, go back to this picture, there's the jetty. The jetty is stopping all that sand from getting its way down the coast. It's piling up behind here. They dredge it, they move it somewhere else. It never actually gets to the Pinery, which is just to the left. Now, there are areas in the Great Lakes where dune recovery will occur. This is a great little example, and I cannot remember the name of this little cove at the moment, but this little cove just south of Kincardine has no dunes, well, very minor dunes right now. And that's because in 2020 they got eroded during the high water levels. But during the low period in the early 80s, the beach used to be way out here. And as a result, there was enough dry sand for the wind to blow and the wind to blow into those dunes. And these dunes got to about 2 to 3 meters in height. And then 2020 took them out again. And it needs to now have the water level drop. So it's possible that these dunes will get a supply of sand if the water level drops far enough. But right now, projections for the Great Lakes with climate change is that we are going to get more wet and humid. And because we're having less lake ice, during the winter, we're evaporating more water, more snow. More snow means that we are actually depleting that water level during the winter, but we're increasing it through the summers. So you get places like Grand Bend, which are completely losing, that's not Grand Bend, sorry, this is Kincardine. They're completely eroding their dunes, and they're not going to have the natural ability to come back. Or places like Southampton, who are building dunes. These are not dunes, but they are pretending they are dunes. And there's a program called the Blue Flag, and if you've ever gone to beaches around the Great Lakes, you'll see this blue flag flying. And all they have to do is put a pile of sand and some vegetation and call it a dune, and they get a blue flag. It's not right. That is not a dune. That's not going to protect the shoreline. That is not a bank of sand that will be used to protect and allow the beach to recover. Here's another example. This is Grand Bend. There's their dunes. Artificial. They don't work. They're not going to protect anything. They're not going to protect it against coastal flooding simply because you've got a big gap right here. So they don't work for flooding. They don't work for erosion. And they're really not habitat because there's a rock wall right there. So we're building these things that are not going to actually protect the shoreline. Where this all starts to come together, I'm going to now move into Lake Erie. is that we have things that are called sediment transport pathways. So depending upon the way in which the waves approach the shoreline, you're going to be driving currents, and those currents move the sediment along the shoreline. And these are called littoral cells, in an area where you're moving that sand back and forth. And a large part of what I've been speaking to has again been towards this Kingsville, Leamington area, and I've shown you some of the cliff shots up into the Central Basin. But this is an example of what the Central Basin looks like. These cliffs are failing, and I'm going to show you a house here in a second. That property, that is about to have a slump failure. You can see that there's a difference in elevation through the trees, and then there's a bit of cracking right here, right by their patio. That's about to fail in one large mass movement. And that movement moves into the sediment, and this area is typically filled with debris as well as very fine particulate matter. It's very, very cloudy, simply because this area is eroding so fast. These are old glacial till bluffs from about 10,000 years ago. So these are eroding in. They're not only just affecting properties and moving at a very fast rate, they're also providing a supply of phosphorus that in Lake Huron may be helping to drive algal blooms, but in the Central Basin of Lake Erie may be helping to drive diatom production during the winter that helps to lead to the hypoxia. So this is not just about people losing their shoreline. This is about the overall health, the water quality within the Great Lakes. And you get places like this. This is one of the most fascinating spots that we found along the Central Basin. This massive gully that has started to develop. You've got this cliff that's failing and these major slumps that are happening, and then because of changes in hydrology, after major storms, or in this particular case, they reconstructed a highway and redirected a stream, and this became the impact. All that sediment coming out of this gully into that water system. Now, some people believe that that's really important, because just like in the Pinery case, all that sand that is being eroded from the cliffs here in the Central Basin go to Long Point, and Long Point is surviving because of the bluffs. No one has ever measured that. It is a diagram from the 1940s that somebody drew an arrow. They drew those arrows on a map and said that sand must move from the bluff to Long Point. So if you're losing your house, you're losing your property, what are you losing it for? Well, is it Long Point? But if it's not Long Point, why are you losing your property? But is there a way to stop it? Here's an example of what's been happening in this area just around Long Point. This area has eroded by about 200 to 300 meters, and as you move towards Long Point, it's also eroded. So even though the bluffs are failing, and the bluffs are believed to be a source of sediment to Long Point, both of them are eroding at an extremely fast rate. Therefore, the bluff retreat is not contributing to the stability of Long Point. You move a little bit further, you start to see a hinge point where, in fact, you are seeing some of these retreats. You get some of these gains. This is not natural. That's a jetty. So in fact, what we're finding is that the sand that is moving along the shoreline may contribute to Long Point, but not enough is getting there, and what is getting there is getting trapped behind a jetty. And when you combine that with river outflows, the bluff retreat, you're helping to contribute to algal blooms and hypoxia. So I'm going to use one last example, Point Pelee. I saw Patricia look at her watch, so I know I have to watch my time here. In Point Pelee. Point Pelee is a historical feature. It's an old feature. This used to be a glacial moraine, a big pile of sand on which this point formed. It is not a dynamic point in which it was formed by waves and currents moving sediment from the coastline. It didn't come from the bluffs. It was there because the water rose and filled in that hill. So when the water was really, really low, it used to be a massive area of a high point. And as the water got higher and higher, it eventually formed to what we know of today as Point Pelee. So it's not a dynamic feature. It's old. Again, with a moraine. So this old shoreline, that is the old shoreline of Lake Erie, back before Lake Huron started to drain into Lake Huron, to Lake Erie. And when Lake Huron started to drain into Lake Erie, the water levels rose, and simply that big hill got smaller and smaller and eventually became a point. And as a result, it's not in equilibrium with modern waves, currents, and water levels. But that's how they're trying to protect it. They're trying to protect it by saying that the sand that is coming from Kingsville, Leamington, Wheatley is what is making Point Pelee, the most biodiverse park in all of Canada. This is what Wheatley looks like, Wheatley Provincial Park. This is actually the highway. The highway actually comes straight out of the picture here. It's no longer anymore. They say that this sand that is coming off of this bluff is providing to Point Pelee. It's not. It's getting trapped behind the Wheatley Harbor. And that Wheatley Harbor, if you see the pile of sand here, that caused this area to erode. And that area to erode, everybody who owned a cottage put up rock walls. They put up rock walls, they have failed, they have flooded. They put up new rock walls at about, again, $10,000 per 100 feet. And now the insurance companies have walked away. So there's no more building, no more sales of these homes, because the insurance company says, we don't want to be part of this. And because of those rock walls, you're now depleting the sand that is moving towards Point Pelee. So Point Pelee is a historical feature that was never dependent upon the bluffs, but it needed a little bit of bluff sediment just to keep it in equilibrium, just to keep it right. Now there's nothing. And these houses have blocked all that sand. But because they blocked the sand and those walls are failing, this is what's typically happening during big winter storms. The water comes up over the rock wall, fills in here. This is their septic tank. So all that water goes straight back out into Lake Erie. And that's why the insurance companies have simply walked away from this region. But here's probably the most dramatic shot. So Wheatley Harbor is up here. Those rock walls are right along here where the houses were flooding. Look at the indentation of the shoreline. That's how much sand and how much Point Pelee has eroded just in the last 20 years. And then this, once you get past the trees and into the marsh, the trees were providing some level of protection. They've eroded even further back. And as a result, Point Pelee is shrinking. But it's not only just shrinking, and this movie's not wanting to work here at the moment, it's not only shrinking, it's primarily shrinking on the eastern side, which means it's shrinking and moving westward. But as it shrinks and moves westward, all of this marsh, so if you're a birder and you go down to Point Pelee, this marsh is one of your most important areas to find for birding. This marsh is constantly now being broken through by the waves, and as a result, the actual marsh area is getting lost. This is what it looks like on the eastern side, just on the other side of the marsh. My son at a much younger age for scale there, and just looking at about a meter of sand that is lost. And you get things like barrier breaching. So to give you an idea, if you go to Point Pelee and you go and you stand on the big bird observatory right there, this is the marsh in front of you. It's now broken through, and the waves and the currents move through. The chemistry of this marsh will change regularly with these water level rises. But what we found when we started to monitor this shoreline is that this has been happening for decades, for centuries. And in fact, that was the old shoreline, that marsh. So if you start looking at these features, you can see that this has been obliterated and recovered many times, which is great, which means that in fact this is part of its normal dynamic system. It's resilient, it's going to break through, but it'll recover. And this place here, which we call East Beach, broke through in 2020, stayed open in 2021, but now it's about half a meter of sand that blocks this entrance. Great. It opens up, closes up, opens up, closes up. The whole thing goes through a cycle. It goes through a cycle because there's sand from adjacent shorelines that fills in the hole. The water levels break through, sand erodes from the edges, fills in the gap, and the whole thing heals. And you got a scar, but the whole thing heals. This is water level on the X here. This is the actual size of the breach. At this particular beach, it goes up, and it comes back down, it goes up, and it comes back down. A hysteresis. Even as water levels continue to rise, the beach adjacent to it erodes, fills in the gap, and the whole thing recovers. Perfect. That is great. But if I go to one other breach about 2 kilometers from that other one, this is called Hillman Marsh, and they're about to spend $20 to $30 million to protect this breach. Those houses with all the rock walls are right here. As a result, that's where the shoreline used to be. This is where the shoreline is today, and it's completely opened up, and this Hillman Marsh is no longer a marsh. They're going to put in all this money. When we looked at this, historically, this did the same. It opened up, it recovered. It opened up and recovered until people put in rock walls, and now it can no longer recover. As a result of the rock walls, apologize for the really bad cartoons here, but for this rock wall, there's no longer any sand, which means that even when water levels start to fall, the breach has stayed open, and this breach will never close. They're again putting in tens of millions of dollars to protect this. And this is what it looks like from the ground. I'm standing on that one rock wall, there's the breach, and this is what happens during the winter now, is that these big waves come in, you're affecting the vegetation, you're ripping it up, you're changing the chemistry, and you're changing the fish species within that marsh. Again, historically, over long periods of time, that's great. That's part of the whole rejuvenation of that marsh. But now this thing will never recover. So what we're seeing in large parts of the Great Lakes is that there are some areas that naturally recover. And there's other areas, because of the lack of sand, they'll never recover. So now they're talking about, in Point Pelee, nourishing the beach. The problem is, when you look at this line where the old shoreline was, that's almost 5 meters deep now. 5 meters deep over a distance of about 5 kilometers. Think of the volume of sand that you would require to fill in that hole. We simply don't have it. Hillman Marsh, they're going to nourish it. They're going to put rock walls to protect the marsh. Opposite to what is needed from a sediment perspective. They're going to put in more of these structures because they're not affecting this. This is the largest freshwater commercial fishery in the world. That harbor is really important. So you can't get rid of this jetty. You got to keep the harbor, and everybody is now protecting their shorelines. So you've starved the environment. It's happening on the west side, but on the west side, it's not as deep. I'm just going to watch my time here. So where do you get the sand? How do you nourish this? It's the end of Point Pelee. All this sand that's at the end of Point Pelee is part of the old moraine, but it used to be in the cliffs, in the bluffs. So the idea now is that we take this sand from the end of Point Pelee and put it right at the very beginning and let it come through. And you basically create a circulation system, a pump, where you take it from the end, you put it to the beginning, and you just keep it circulating back and forth. The problem is, this is the very first set of surveys that have ever been done, so we don't know how much sand is there. So there is a way, by taking the sand here and putting it back to the beginning, we can protect Point Pelee. So I'll go back to the original slide. Can you protect this? Rock wall? No, because that means almost 140 kilometers of Lake Erie would have to be a rock wall. And that's only a temporary solution. And this sand might be needed for Long Point, might be needed for Pelee. We simply don't know. But people's livelihoods, people's homes, including some alumni from Waterloo, they're being affected by this. And that's one of the things that we're trying to figure out, and ultimately where that sand will go. Now that is the main ending slide from this talk, but I want to talk about one last slide. And this is something that I didn't tell you at the very beginning. When Mario was telling you that I went to Guelph and went to Toronto and I did sand, I actually was not going to university for sand. I learned that beaches are really amazing, so I went in the right choice. I was originally going for music and looking at U of T to go into the Royal Conservatory. That's where I was heading. But because of my music background, I look at shorelines differently. And I didn't get into it a lot in this talk here, but when I do a departmental seminar in a couple of weeks, I'm going to get into a little bit more. I look at shorelines and I'm able to extract them and pull them apart in different ways than any other group. And so by looking at the shorelines from PEI, I asked one of our science students who had a music background to put my data to music. This music is that shoreline. It's near shore beach dune, near shore beach dune, near shore beach dune. That's PEI to music. And when you start to see the break in the dune, you'll hear the change in the music. And so one of the programs that we are starting here at Waterloo is called Science Meets Art. And we want more of our students to be able to take their data, to take what they're looking at and put it to music, to put it to creative art. We're creating a drama class for science students. We want students to play both sides of their brain. So with that as a musical background, thank you very much for joining here tonight and for hearing this kind of broad overview of shoreline issues in the Great Lakes, the Maritimes, and the Gulf of Mexico. Thank you.
Thank you so much, Dr. Hauser. And we're going to open up the floor to questions. So is there anybody that has any questions?
I'm from Kincardine. I lived there for 37 years, moved to Waterloo 4 years ago, went to University of Waterloo. Anyways, those two piers, in the last 2 or 3 months, there have been 6 or 7 people have drowned there. Got so bad, I used to be a council mayor up there. The council shut the beach, like those people couldn't go out there. They had a big fence across there. They just opened up, I think, a week or so ago. But I think it's very important that if somehow you could transfer your messages to Kincardine to help them solve that safety issue at the 2 piers.
So in Kincardine, there's a program called Smart Beach that's going on. That is actually my project. So we're the ones that were putting the fencing. We're saying you need to put a fence there. You need to have lifeguards. That's the first line of defense. But if you can't, a lot of communities, I'm not going to say Kincardine, but a lot of municipalities do not want to have lifeguards because they believe that a lifeguard makes you more liable for a drowning. Don't understand that. But that's what their thoughts are, and they don't want to have a lifeguard program there. So we're saying close the jetties, because that is your main point at which people get access to. But there's a lot of people who say, I've always gone to the jetty. That's part of our tourism. There's an economic question there. But when you drive into Kincardine, the biggest issue is that when you drive into the beach, I'm driving into the beach here right now, so I'm driving into the beach, and you automatically turn to the right because that's where the parking spots are. So I'm going to park my car here, you get out, and the main boardwalk goes straight to the jetty. They actually empty you out at the most dangerous spot on the beach. That is not uncommon, and that is because that is where there is no dune, and they want to protect the dune. Pensacola, which I didn't go into it, every main boardwalk, every main parking lot on that beach is at a spot where there were no dunes because they didn't want to put a parking lot on a dune. But as a result, there was no dune because there was a rip current. So there is an entire landscape redevelopment that has to happen for Kincardine. You've got to think about some areas may not be accessible. And then you need some way to warn people that the water is dangerous or not. Because sometimes when you're standing there and you're right beside the jetty, it is flat calm. How do you tell people that's dangerous? But then there's a couple of hours later, it can be a meter-high waves, and you've got a very fast rip right moving along that jetty. That is the problem. But again, only 7 beaches in all of Ontario have lifeguards. And the bigger issue is we need more lifeguards in the province. So I completely agree with you. I'd love to talk to you more after. I think there was a question. Yeah.
Earlier, you said that the beaches and that take about 10 years to recover. You've got all these storms year after year. Why isn't it getting pushed back further? How can it recover?
we're seeing this all happening in real time, and that's part of the problem, is that we have not had enough people studying these recovery processes in the past to know what's going to happen. So that data of 10 years of recovery was the first of its kind, and it was from 2004 to about 2014, 2015. We're now using the Coastie program to look at the recovery of after Hurricane Fiona. We actually started after Hurricane Dorian, then Fiona came, and then Lee came. This is part of the problem, is that it's going to happen very quickly. Now, you need hurricanes for barrier islands to survive. Because if water levels simply rise, I was driving my car a second ago, I'm now going to be a beach. I'm the dune. This is a teapot. So the water level is going to rise. Eventually, I am going to flood. But the only way to get my sand back and higher up in elevation is to have the storm scarp me, erode me. The wind pushes that sand on the scarp backwards, and when the sand comes in to recover, it fills in a little bit further landward, a little bit further up. So it's a Goldilocks problem. Too few storms is a problem. Too many storms, too frequently, is a big problem. You need to have just the right amount of storm activity. We don't know what that means. We know the extremes, but there's some spot in the middle where we do need some storm activity, but not too much of it. Not too hot, not too cold.
What's the role of vegetation on the dune in terms of protecting?
The main role of the vegetation is to collect sand during the recovery process. So when the dune gets eroded, it wipes it out, but some of the little pieces of vegetation, the root system, regrows that vegetation, and it creates a drag on the wind, and then when the wind is coming across blowing sand, the sand gets deposited inside the vegetation, and it starts to regrow, and the vegetation grows with it, always providing that protection from the wind. During a storm, the vegetation provides very little, if any, protective role. It is just simply ripped out. So its role is in the recovery process, not in the storm impact process. However, some recent work done by Texas A&M in a flume suggests that vegetation, because it can pull apart, and basically, if you imagine you're taking some cement and you pull rebar apart, you can actually pull it apart faster. So now they're suggesting that vegetation is good during recovery, but bad during storms. Again, we haven't had enough of these to be able to understand what that answer is.
Maybe we'll take one more question and then we'll head on.
There is beer and wine at the back. Not the back here, out in the hall.
Has there been any study of any effect on climate change on all of the Grand River Basin and the amount of sediment it puts into the lakes?
There are people who are working on that. I don't have enough information on that. There's other people in the room who might have better information about how those river systems are moving sediment out. I don't know that myself, unfortunately. Can we have one that I can answer? Any others?
You showed a gully on Lake Erie in one of your slides.
Yeah.
I know of similar features on Lake Huron that are, at least from the air photos, minimum 70, 80 years old, likely older. I'm just wondering if you know how old that gully on Lake Erie is.
It's about 10 maximum. That's it. And it was all due to construction adjacent to that farm field, changed the groundwater flow, sapped it at that spot right at where the gully had formed, and it migrated back within 10 years. A big volume of sand that moved out. So very different process than what you've been looking at in Bayfield area. All right.
Okay, thank you so much,
Thank you.
everybody, for joining us. Thank you, Dr. Hauser, for sharing your research with us. And of course, we'll welcome all of you to join us in the foyer for a casual reception. And if you have any other questions, I'm sure Dr. Hauser would be happy to answer them there. Thank you.